The next couple of slides, I want to go over the performance. So the first thing is just assessing kind of the overall bias. So I didn't mention previously, but we split our data set to like 85%, 15% into a training and a validation data set so that we can see if the model is improving data that was independent of how it was regressed. And in this, I'm showing the overall bias. So we want to be as close to 0 as possible, which I'm kind of illustrating where 0 is with my cursor. The black is BSSA 14, the blue is with the proposed model. Solid line is the training data set, dashed line is the validation data set. And in both cases, for training and validation, the proposed model does a better job than the BSSA 14 model. There's a period range between like 0.5 to 1 second or so, where the proposed model does slightly worse. It's slightly more positive than the BSSA 14. But for the most part, the model does a much better job than BSSA 14.
And a better job is judged by being closer to 0.
Exactly.
Okay.
And this can also be seen if we see those same plots from before, but with the updated model, where for all of the events, we're right on 0 for our bin means with distance. For magnitude greater than 5, we're a little bit better than what we saw before, which is great. And for magnitude less than 5, we're doing much better than what we saw before. So we can see that we've corrected for those path effects at an average scale. If we want to look at it at that kind of sub-regional level that we saw before, we can do the same thing. And in this case, the results aren't going to be perfect because we had to smooth the model. But you can see if we just focus at the far distances, we're pretty close to 0 for our bin means and all of the subregions, and this is consistent for other intensity measures also. So this is doing a great job to show that by accounting for these subregional variations in the inelastic attenuation, we're correcting for these systematic path biases.
But that's because you use this data to develop the model in the first place, right?
Yes.
Okay.
But this is also true for the validation data set. There's just a lot less data points, so it's less impressive. If we want to look at a space that we're a little more used to in intensity versus distance space, here we have data from North Coast events that just stay within the North Coast. So you can see this is the BSSA 14 prediction by the shaded region from magnitude 4 to 4.5. You can see we have gross overprediction at intermediate to far distances, whereas the proposed model does a good job of capturing the average between these observations and a really good fit at far distances also. So this is kind of a more classical illustration of how the path effect model captures the data in a space that isn't contaminated by other path effect, by other properties of the ground motion model that you choose to use. So then I want to lead into a discussion of dispersion and variability. So this comes from our mixed effects regression. Just showed the equations here before, and I just want to define a couple terms. The first is our total variability, which is essentially the standard deviation of our total residuals. We have our between event variability, which is the standard deviation of our event terms, which are the event-specific biases. And we have within event variability, which is the standard deviation of our within event residuals, which can be separated into site-to-site variability and single station variability. So the important thing that we're going to look at are all of them, obviously, but the single station variability is, in theory, contains within it the path effect variability. So first, I want to just demonstrate the effect that increasing the data set has on our standard deviation, our dispersion terms. So this is just for the BSSA 14 ground motion model. The thick lines are total standard deviation, the dashed lines are the between event, and the dotted lines are the within event variability. The gray lines are the NGA West 2 data set, and the black lines are with the expanded data set. We see at short to intermediate periods, about 1 second, that we see an increase in the variability. This is because of several factors. One is generally when you add more data, certainty increases, but also because we've added a lot of data in new parts of the state, so the diversity of our data has increased, which is driving that uncertainty. However, at long periods, we see a reduction, which is mostly driven by these event terms, by the dashed line, which is going to be the between event variability. You can see it actually is reduced. This is driven because we have so many more stations now for events, and the sensor quality has improved to where we can use our observations at much longer periods. So we have much more data in the new data set to our availability so that we can better estimate the ground motion coefficients at longer periods. This is also combined with the fact that most of what we think of influencing ground motions is true for short to intermediate periods. At longer periods, there isn't much that really has strong impacts. So because there's not a lot of strongly correlated predictor variables, in other words, at long periods, it's relatively stable necessarily, with except for maybe side effects related to base and structure and stuff like that, that it's less complicated than the short period ground motions. So the ground motion model was doing a pretty good job in the first place at longer periods.
So what I walk away with what you just said was that the less you know, the more certain you are.
That ignorance is bliss, exactly.
As our circle, I think the deGrasse Tyson guy was saying, the more your circle of knowledge increases, the more the radius of the circle of knowledge increases, so does the circumference of ignorance. And so the more you know that you know less. So it's an interesting phenomenon here, but I do like the point that you're making about the longer period, that we're doing a better job in measuring it right now more than just anything else, and therefore we can do better in modeling it.
Yes.
So interesting.
So here I show the computed values for the total between event, within event, and single station variability from before for the training and validation data sets. Again, black is for the default model, blue is for the proposed model. And in all cases, it's consistent between the training and validation that we see a reduction in the variability. The reduction's the biggest for the total standard deviation and also for the between event. So this is highlighting how previously path effects were really contaminating the event terms that we were estimating, especially in the North Coast events, and also it was pretty significant for the events that are in Eastern California. We saw significant bias because of path effects. So because we correct for those, our event terms were much more certain of their accuracy, that they reflect the event-specific bias just for source effects. And that's where we see the greatest reductions. But we also see reductions in phi, which is driven by the phi SS term. One thing related to this is there are models that give us these uncertainties that we can apply for hazard calculations, for example. Even though we see this reduction is offset by that increase that we saw previously on the previous slide. So because we have more accurate results, they're just as uncertain as they previously were. It's just that they're less biased. So we don't propose any adjustment model for the ground motion model uncertainty terms, because these uncertainties that we're calculating are consistent with what the NGA West 2 models had previously. This can be highlighted by, and also, I also want to mention that even if this reduction doesn't look impressive, it actually is impressive because the reduction occurs at far distance observations, which would be the solid line observations greater than 100 kilometers. We can see reductions up to negative 0.08 in log space for the phi and phi SS terms. So the reductions, this shows for all data, which includes short distances and long distances. But if we look at just the long distances, that's where we see the greatest improvement of our predictions. And I think there was something else I wanted to mention, but it slipped my mind right now.
Let me ask you a question then. The variability between your training and your validation set, it's going down because you have less data, right?
Yes.
Okay. But the trends are the same, and the comparison between the black and the blue is the same, and that's what's important.
Exactly.
Okay, cool. And so then that's the versus period on the left. And you're saying even though it's going down, it's really going up somewhere else. And so then you transition on the right, which is the change in the phi. So before we were actually looking at the absolute value phi. This is now how much it has changed. And you're saying it's changed the most, because remember the zero's up high, the most for the longer distance ones. And the way I see this intermediate period range, that's where the peak is. And so, yes, it's for the largest values. And so it's where you will have the biggest impact. Is good to have it there.
Yes.
And so the top and the bottom, the total phi is, and versus just a single station phi, right? Why are you separating the two?
So total phi contains within it site effects and path, or site uncertainty and path uncertainty. And
Okay.
so the phi SS is where we would traditionally attribute most of the path uncertainty. So you can see not all of it, not all of the reduction can be attributed to phi SS. We saw previously how I showed how site terms also change when you correct for path effects. So there's a small reduction in uncertainty for the phi S2S. I just didn't illustrate it on these plots.
Okay. And so the net effects are, there's so many variables, we can't really make a prediction on the net effect, but we're improving all these different components and improving the variability. Okay.
So we essentially have the same uncertainty as we did with the NGA models, the NGA West 2 model, but instead of predicting the same value for everywhere in California, now the median prediction has changed, but the uncertainty has stayed the same.
And the average of the medians hasn't changed, quote unquote.
Yeah, exactly.
Interesting. That's important. So, okay. So we're not, well, I find it interesting because these models you're not discrediting the NGA West 2, you are just changing the shades of the colors within it. Where is it going to be higher? Where is it going to be lower? The net effect is like your residuals is going to be 0, but where do we make it more specific on, kind of spreading that average into something a little bit more detailed? And yeah, and it's interesting because that's the, it's not the variability, it's the epistemic. It's not, is this does this fit into the epistemic uncertainty, or does this fit into the aleatory variability? Okay. All right. That's important. That's a whole other lecture.
Yeah, that's okay. We don't have enough time.
Okay, cool.
So the last thing I'd like to do is just present a simple comparison between cell-based and subregional models. So on the top, I'm just showing on the left the subregional model that we have. I've colored the subregions based off of whether they have slower than average attenuation in shades of blue or faster than average shades of attenuation in red. And on the right is the Kuhn et al. Model. The Kuhn et al. 2019, same coloration. The scales are exactly the same for the colors. The one thing I'd want to mention is that I can't perform a direct comparison between these two models because there's too many differences. One difference is we used a much larger data set, whereas the Kuhn et al. Model used only NGA West 2 data. Another difference is we used the BSSA 14 model. Kuhn et al. Used the base ASK 14 ground motion model. And then also there's slight differences in how the coefficients are themselves regressed. So it's difficult to perform an apples to apples comparison, but we can look at things a little bit quantitatively and highlight a couple features. For the most part, what I'm going to illustrate this example by using 4 paths. Paths 1 and 2 travel across a couple subregions in Northern California where there wasn't significant data in Kuhn et al. So when they did their study. So they don't have much adjustments. Most of the adjustments are pretty close to 0 because they just didn't have data. So they're just taking essentially the statewide value that they assigned at the beginning of their analysis. Path 3 travels through entirely the Sierra Nevada subprovince that we have in a region where Kuhn et al. Had a lot of data. And path 4 rather, which is in the pink, travels entirely in what we call South Coast, which is Southern California, where Kuhn et al. Also had significant amount of data. So if we first just look at the paths where Kuhn et al. Didn't have data, which are paths 1 and 2, the black lines are the base ground motion models. You can see, and the dashed lines are our proposed model, and the dotted lines are the Kuhn et al. 2019 predictions. You can see that in both cases, the colored lines are offset from the black lines, which suggests that both models are altering their base ground motion models, which is as expected. But I want to point out that the Kuhn et al. Model does not really predict significant changes between whether you're path 1, which is green, or path 2, which is orange. They follow pretty much similar trends. There's some slight differences, but for the most part, these are the same prediction for these paths. Whereas our model has pretty big differences. We see a log difference of about 1, almost 2 in log difference, which is huge, whether the path travels through the North Coast or travels across the Sierra Nevada and Central Valley part of the state. Now, we can't say with certainty which model is correct, but this highlights that our model can now capture the average trends in areas where Kuhn et al. Model does not have good resolution. Now, to test that, because I used the word average attenuation very carefully, we have paths 3 and 4, which travel entirely within one subregion where the paths have good data in Kuhn et al. So first, starting with the pink, which is the path through the Sierra Nevada, the dashed and the purple lines are pretty close to each other. There's some offset, but for the most part, the final predictions are really close to each other, and the lines follow generally the same value, which suggests that this Sierra Nevada subregion captures the average attenuation pretty well, even when looking at a much finer resolution. Obviously, there's going to be some variation and different changes of slope, but the predictions are pretty close to each other. If we look at path 4, which travels through Southern California, this geologic domain is a lot more heterogeneous than the Sierra Nevada. Sierra Nevada is a mountain range, kind of a big batholith structure, granitic rock, pretty competent, pretty consistent, we would assume. The South Coast has a lot of basins. We have LA Basin, San Gabriel Basin. We have some mountain areas like Santa Monica Mountains and so on. And so because of this diversity, maybe there's some sub-subregional differences. And that's exactly what we see when we look at the pink. Now, the final prediction of both models is almost exactly the same. This highlights the fact that our subregion captures the average attenuation of this area. So there may be differences at short paths, but if your path travels over that entire subregion, you're going to be modeled pretty well using this subregional approach. You'll get the correct value. But if you take short paths, or only paths that travel part of the subregion, you may see some bias. So this leads to kind of an important topic, which might be that maybe subregionalization needs to be refined in certain areas where we do have good data. So the Bay Area and South Coast, we should go smaller. We should make smaller subregions. Areas where we don't have a lot of data still, like in the North Coast, it might be fine to use a large region, but if you have a lot of data and you can confidently do it, go smaller. But try to incorporate physical constraints so that your regions are internally compatible with all the properties that they have. I want to pause here if you have any questions related to these figures.
No, I find it fascinating, and it's almost like, I like the idea. I mean, it's just, again, it's just refining your mesh.
Mm-hmm.
And so I appreciate how you're showing that they're just different. And, you know, when you need a finer mesh, then the finer mesh one will do better. But when you don't, or you can't quite rely on one or the other either, it becomes very much dependent on the path,
Yeah.
on the type of path. and so it's fascinating, but also it's interesting because I feel like as you said, Southern California has basins, and therefore those would be served better by sub-regional and localization. But then wouldn't you take the basin into, see, the way I would see it is if your station is in the basin, it's one thing. But if you're just traveling under the basin to my site, is that basin really going to impact? How shallow is your basin? And so what do you do with a basin is important, because do you put it into your side effects or do you not, or do you put it into your path effects, right? Which goes back to the discussion that you were having before. And so it's fascinating because there is a third dimension into the plane that affects how the waves propagate. So, yeah.
Great. So then I think the last thing, I just have a couple conclusions that I'd like to end on. I have some general conclusions about path modeling, and then I have some more specific conclusions related to the work that was shown here. So first, with some general conclusions, path models exist on an ergodic non-ergodic spectrum that is a lot wider than the site response or the site effect modeling spectrum. Subregional path modeling combines the advantages of regional and cell-based methods. By that, I mean we take the physical constraints of your variation spatially from regional models and combine it with the robust mathematical approach that cell-based methods use. And so that's something that really hasn't been done necessarily, but I think that's a big step forward for the cell-based methods. And kind of as with other modeling methods that use data, we're limited by the data availability. That's true for pretty much anything any empirically based model. When it comes to California, big findings are we see variable rates of analysis attenuation across the state, significantly higher than average in the North Coast, lower than average in the eastern parts of the state, being Sierra Nevada and the Eastern California shear zone, and kind of intermediate rates for the other subregions that may trend slightly to be higher rates of attenuation. The current models are dominated by small magnitude data, so it's kind of an implicit assumption that we assume that these variations are applicable for large magnitudes. That's kind of yet to be seen. I don't really know of any studies that have looked into if there's nonlinearity effects in path effects. I think that'd be interesting to see. The unfortunate side of that is I don't think that we have enough actual data to look at that confidently, so we need to kind of lean into the simulations, which have their own set of drawbacks. And we see a significant reduction of variability that's most significant at far distances. That can be achieved using the subregional method that is pretty similar to the cell-based method when we've compared our results to the Kuhn et al. Model. But if you look at smaller paths in between, it might not be as, the predictions might not be as reliable. And so that leads to the last statement, which is that further refinement of the subregions can hold significant potential to bring us to a practically non-ergodic path model by leveraging physical constraints during our regionalization with the robust math behind cell-based methods. So then if you're interested in seeing some of the references that I've throughout the presentation. And then the last thing that I'd like to mention is that the work related to the model and some of the background information is also presented in the introduction section of a paper that we've submitted to the Bulletin of the Seismological Society of America, or BSSSA, and hopefully that'll be out in publication soon, if you're interested.
Wow, that was excellent. So I appreciated it. So
of course, and I appreciate you having me on your YouTube channel.
This is the first time I do it like this. So, because I see so many people that do these podcasts and things like that, which is kind of what this feels like. But I like to stay technical. So I think there's a lot of neat stuff to talk about it. But and that was kind of my point, is to go a little bit deeper and talk about, we were not constrained by time. I'm going to cut this video into bits and pieces, but I think you covered a lot of interesting topics that I would watch the whole 3 hours in a row.
Yeah, and you had excellent questions. I think it really helped your viewers to understand things
Yeah, I try to go down to the basics, pretending I didn't know those things, but well, it helps because nowadays it's becoming part of our vernacular. Is that the right word? And so I think it's important for people to understand all the different components. So this was excellent. I appreciate your taking the time to meet with me, and hopefully we'll do this again with some other topics that we
Yeah.
could learn about. So
Yeah, I would
excellent.
love to come back.
Oh,
Yeah.
cool. All right. Thanks,
Right.
Tristan.
See you
All right.
later tonight.
Thank you. You will. Oh, yeah.
Yeah.
Bye. Bye-bye.